Okay, we're live and recording and officially ready for Software Engineering 2. And okay, so first order of business, I want to go through assignment number 4 by request, answer any questions by request, and talk about the final exam, and talk about the schedule for the next couple weeks, and talk about topics and things of that nature. And then we're going to finish up the Cosimo model and some of the other metrics related stuff, and then get into architectural designs and take a look at that, which deals with the fourth assignment. So if you haven't noticed, I posted the final exam schedule on the website. That is available for you. And the final exam for this particular class is going to be on software engineering. It's going to be the last, here we go. Nope, that's the wrong class. It will be software engineering weekday section. Oh, there we go. 4:20, Wednesday 4:20, which is, I think I have my little calendar up here somewhere, is, let's see, make that a little bigger. So today is the 30th, excuse me, 4:20 is right here. This is this week, so we have 2 weeks left, 2 more weeks after this week, which means on April 13th, is it April 13th? April 13th, we're going to be reviewing for the final exam. Haven't written the final exam yet, so I don't know what kind of questions. It will be multiple choice, I can tell you that. Probably about 25 questions, but what exactly is going to be on it, you'll find out on the 13th. It's also our WASC accreditation day, so we'll have people roaming around the building from the accreditation board. Hopefully we'll be set up in the joint seminar hall, and hopefully they'll see a bunch of students sitting in a classroom, I hope. So if you show up, it's twofold. Number one, if you show up for software engineering, you're going to be part of the accreditation, hopefully, and you'll be giving us bonus points because we have students to represent students that look like they're taking a class, hopefully. And number two, you'll find out everything you need to know for the final exam. And I'm going to give away all the answers. No, not really. I'm going to give away everything you need to study for. We've covered a lot of topics in this class, so to narrow it down a little bit, tell you which PowerPoints, stuff like that, which information, which topics. I would have already written the exam by then, so you'll hopefully get a good way of studying. And it's a good week before. It's 1 week before the final, so it gives you a whole week to kind of go through. If you don't like the final exams that schedule the date you were scheduled on and you want to switch it, you can send me an email message. If you notice, we're broken out into groups. We got group 1 through 5. We actually have a good number of students in this course, so it has been divided out to make life easier. You want to bring a pen or a pencil with you. You don't have to bring anything else. And it's closed book, closed note, closed internet, closed neighbor, closed everything. And what else can I say about it? You'll have to bring your student ID. You can only show up one time with one ID to take one exam per person, which means you can't come in and take exams from multiple people with multiple IDs, kind of like how you do the check-in on the rosters. You can't do it that way. If you want to take multiple exams that you are taking for yourself for classes that you are enrolled in, you can do that all in one sitting if you'd like. So let's say, for example, you're in this class and you're also in the Oracle class. You want to take them both. You probably want to take it at a later date, but you want to take them both at this time, you can do it. So just let me know ahead of time. Send me an email message, your name, what grouping you're in, what grouping you want to go to. If you refer to group 1 and you say, hey, I'm in group 1, and you don't want to show up at 9 o'clock in the morning. Instead, you'd like to take group 5. Can you switch me from group 1 to group 5? I'll say, okay, good. Because what we're doing is we're going to put together these little roster lists. And when you come to the exam, we're going to check your name off of a list. So if we know where to put you, then we don't have to mess around with finding you somewhere on some scheduled time that wasn't this time. So we can hopefully generate some decent lists. We'll see how that works. But you can download it and you can take a look at the final exam schedule. I also am teaching Software Engineering 2 on the weekend schedule, and the weekend exam for that class is not until the end of April. It's not until April 30th and May 1st. If you need more study time, you could actually go to this one instead. Also, you'll notice on Sunday we have makeup time groups. And we have a makeup time group here on a Saturday or Sunday of the weekend of the 14th and the 16th and the 17th, which isn't going to help you because that's before the 20th. If you're interested in how long the exam will take, it'll be about an hour to an hour and a half. Your time slots are in 2-hour time slots. If you need more time, you can have more time. You just sit longer. We're not going to ask you to. We're not timing you. You're not going to be asked to leave after 2 hours, because we also have some students who will be taking multiple exams in the same sitting. So it's really hard to control that anyway. But you should have as much time as needed. If you request more time, you just stay longer, essentially. Questions about the final exam? Nope. Y'all was going to show up on the 30th. I have a lot of students right now requesting to show up on the 30th and on the 1st of May. Only problem with that is if you wait till the very, 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 very last day and you get into a car accident or your car breaks or your ride breaks or you get sick or you decide you want to leave early to go back, then you end up getting stuck. You do have to take the exam in person. If you have friends who aren't here right now, probably, who are going to say, oh, I have a job, oh, I have a this, I have a that. It doesn't really matter. We don't actually grade you on attendance throughout the entire course. The only thing that I request is that you show up for the final exam in person to take it. So it cannot be done remotely. So if you can't take it, you have a problem, or you know someone in that situation, they'll have to get an incomplete in the course, and then the next time they come to register, they can take the final exam, or they can take it when the next time they're at ITU. Hopefully they will be at ITU. But as part of accreditation as well, we have to make sure you've shown up at least once, and so the at least once is the final exam. So you can't really get out of that. So if anyone is asking, I've already had a couple people already ask, and I've heard a lot of good excuses. But the response to that is, show up the next time you register for classes, or show up next year if you can't make it, and we'll fit you in, and you'll just have to get an incomplete, essentially. But nobody wants an incomplete either. So, questions on the final? No? Okay, good. So if you show up on the 13th, you'll get everything you need to know on that. I had a student request some assistance with assignment number 4. So I'm going to go over assignment number 4, and I'm actually starting software architecture analysis and design today as well, which is lecture number 10 and 11. I'm going to focus on UML, considering that that's probably going to be the most popular technique these days. So what I'm looking at here is assignment number 4, and again, all the assignments will be due May 9th or something like that, so way after the final exam. All the assignments are due the first week in May, I believe, but the TAs will be sending out the exact date on that. So you're asked to develop the architecture for a mine pump control system. Mine, like for coal mine. Designed to monitor the pump. Oh, this is for water. The pump flood water out of the mine shafts as underground mining operations take place far below the water table. Flooding into the mine galleries and shafts is an ever-present danger. Okay, you can read about mines online if you're not familiar with the concept, or you can make up your own concept if you want. I don't really care. Your own interpretation of what the mines are is sufficient. But you want to get rid of the excessive flooding. It's clearly a safety hazard for workers, but also profitability implications ranging from equipment damage, productivity delays, mine closures, extreme circumstances, problems that occur. So the system to be developed will be required to monitor the water level in a given mine shaft using 2 sensors. And actually, how much longer does this go? This is a pretty long description. I'm not going to read this. It could take me all class period to go through the entire description. But the concept is you're reading through this description. And it's got some sensors. It's got some requirements. You go through and you read through the description and the requirements. If you don't understand some of the details of it, make it up. Make some assumptions. What are these sensors? Oh, they're magnetic sensors, or they're water sensors. I don't know what water sensors. Chances are you probably have not worked in this domain yet. You don't know anything about, or maybe probably never will, anything about mine shafts, perhaps, and flooding. I don't even know about that. But your goal is to, your task is to document the software architecture of this particular system. And the course lectures can be used as a guideline. Those are the ones we're going to start today, actually. And you can also find some useful information at this particular link, which I believe still works, which diagrams out software architectures. So you can use any development technique, and any's in caps to kind of add focus to that you'd like. Provide a complete design of the system as described above. All right, so this assignment is left to interpretation. So you're interpreting the requirements, you're interpreting the design. The concept is to give you practice putting together an architectural design. And what was an architectural design? Well, an architectural design is the architect of the system. Its components, its modules, its functions, it's however you want to define pieces that are going to be put together to create this system. The system might have hardware, the system might have software. Hopefully they're both working together, sharing information, exchanging information. And they're designed as a complete system. System meaning a combination of all of the subparts that compose the system. And today I'm actually going to start in with object-oriented architectural designs, and I think probably by the end of the lecture, because I'm going to spend hopefully a good 45 minutes to an hour going over architectural design as a concept, you'll get a better understanding of the particular requirements in terms of what you have to put together. That would be the content, the quality, the context, anything you want to do. So you might be questioning, well, do I need to write a report? Do I need to put together diagrams? Anything you want to do to explain the concept. There's no minimum or maximum word requirement. There's no word requirement on here. It just says to put something together. So you could take a couple of different approaches. If you're not familiar with diagramming, don't want to tackle any of that stuff, you could simply describe it and write, give me a description, however long the description might be. An easier approach might be to come up with, and we'll be talking about that, I'll be talking about it momentarily, an architectural design in terms of UML, class diagrams, or some sort of architectural structure in another methodology that you might be familiar with. It doesn't have to be one I've talked about in the class. It doesn't have to be, it could be anything particular that you want. You have freedom, academic freedom, to think about and come up with an architectural design. And what I mean by architectural is everything, the system architect. Because you're mapping out, you're designing the system. Take the word architect out of there and just say designing the system. So, did that answer your question, or did you have something else I didn't talk about? Nope. Okay, we're good. Anybody else have any other questions on assignment number 4? Everybody do it already? Anybody started?
Getting sleepy.
You're getting sleepy? That's the hypnosis. You're feeling sleepy. I think it's the lack of air in this building. I've already decided I'm going to think I'm somewhere else. I'm not here right now, so I don't have to worry about this building. But I believe next week we might be in a different room. I hope the seminar hall might be finished by then. I'm not liking the aura of this building, or this room, I should say. If we get too stuffy, we can open up the door. You guys, it actually did start getting a little muggy a few minutes ago. Does you in the back? Do you want to do me a favor? Anyone sitting back there and prop that back door open? You're right. The air is kind of thick. And you know, it took someone to point it out for me to actually notice it. Actually. Oh, much better. Okay, so I want to quickly finish up this lecture. This lecture was talking about estimating, and I stopped here at this point in which we introduced this Cosimo model, and some of you may have heard of it already, and some of you might think it's junk science, and a lot of people actually think it is junk science. Instead of coming up with an estimate and kind of just put us back on track, I kind of skipped through it already, but we covered this last time if you missed it. These were estimating techniques, how to figure out how much something is going to cost, how long it's going to take, different ways of measuring using metrics on the software itself, looking at different laws, pricing to win, top-down, bottom-up estimations, all sorts of different techniques associated with costing and calculating uncertainty, because we really don't know what something is going to cost or how long something is going to take until we actually put it together. So the Cosimo model takes a slightly different approach to it, and it looks on previous experiences and uses the previous experiences to estimate future plans. Seems like it's a little bit more promising. It's been around since the early 80s. And here we have 1981, the first model came out. So it's an empirical model based on project experience. What's going on now, what has happened in the past to predict what's going to happen in the future. Well-documented independent models and which are not tied to specific software vendors. So it's kind of an independent approach to estimating. Long history from 1981, as I mentioned. And this is not even the current version. COSMO 2 takes into account different approaches to software development, reuse, object orientation, stuff like that. But it's not a full object orientation model. It doesn't work well with object orientation. So, long story short, it's an outdated model. Everything is object oriented these days. I mean, 90% of your projects are. So this model works well when you have things of complexity you can measure. It's hard to measure an object oriented architecture, as we're going to see. So what I want to do is kind of go through some of the little features, introduce the model to you so you know what it is in concept. You probably will never apply it. You'll probably never use it. There might be some old companies using, who have implemented this model and have used it successfully. Those who have been able to implement it have found great success with it, which is why it's around. It's been around since the 80s. Here's an example of the COSMO 81, which is the primitive earlier part of it, looking at project complexity and putting it into a category by applying a formula where you've got a project model which is going to be essentially put together to equal a simple, a moderate, or an embedded type of environment in terms of the complexity. And if it's a simple project, an example, the description, you have well understood application developed by small teams, you're going to apply a formula. And so that's why I say it's kind of the junk science route. Not really junk, but you're going to develop a formula to tell you from previous experiences what's going to happen into the future and how you can apply it midway stream through the project and kind of estimate. Look into. It's better than flipping a coin. The COSMO 2 is a 3-level model that allows increasing detail estimates to be prepared and throughout the developing process. We wanted to leave that door open. We wanted to. Yeah, it was getting a little muggy in here. Thank you. So prepared as development progresses. So the earlier one took the more current version of the revisions of it are looking at it as a project is developing as it's progressing. Earlier prototype level, earlier design, post-architectural level, kind of estimates that are made. And I think of it sort of like a scientific approach where a formula is developed and you apply the formula, you plug the numbers of the current state of the project into the formula, and you get a trend or you get information that's going to tell you about the rest of the project, theoretically. Supports prototyping projects based on standard estimates, takes case tools into consideration. In fact, you can load the information into the case tools for the most part. If you're not familiar with computer-aided software engineering, another term that's very outdated as well. Nobody uses case tools anymore either. But if you're using case tools in the COSMO model, you got to use them together and automate the process of coming up with these estimates. In terms of the formula, I'm not going to go through the formula, actually. So it's the effort per person, months, and the number of object points. If you remember what I talked about last time, I talked about function point analysis. It looked like function points, modules. You can even use it for object points as well to count different components or pieces. And it gives you a complexity measurement depending upon how many internal, external, how many function points there are. You add it all up, you come up with a complexity measurement. Same concept, except for you're applying it to different characteristics outside of function points. So looks at, gives you the man hours, persons per month it's going to take. So you can apply the formula in this particular example, persons per month is going to be equal to, something, some estimate. And we'll leave the formula to your imagination. The formula is actually kind of the junk science part of it. How can you really calculate? What are you counting? What are you adding together? Hopefully you're not going to be adding together lines of code, hopefully. If you use function points, you're going to be a little bit more accurate, but still you're definitely going to be making a formula out of something. Object point productivity is just like function point in terms of looking at very low, low, minimal, high, very high, and on a scale of developers' experience capabilities, maturity capabilities, and all sorts of different other criteria that you might be applying towards it. So in the early, actually I'm going to kind of skip through this because you're not going to be required to know anything about the Cosmo model for the final exam or for this class, but I kind of wanted to give you at least a little bit of an overview of it. So if you heard the term, think of it as a way of estimating out complexity. Time is going to take for man hours and for how difficult the project is actually going to be created. And it is one of the oldest models out there, actually, if you think of it. So you can go through the slides that actually starts, if you're writing this down, it's slide number 9. The Cosmo model starts really at slide number 38, actually, and it goes to the end. So, but for purposes of this class, it's kind of in there as notation, but don't. If you have an interest in knowing about it, go for it. Otherwise, it's not going to gain you any insights into anything. What I really want to cover today is Lecture 10, and Lecture 10 is looking at architectural design starting out with objects. So we have the designing the system itself using self-contained objects and self-contained, object classes. We all know what objects are, and the purpose of this lecture is not actually to give you a complete object-oriented design exposure. In fact, if I could do that in an hour, that would be fantastic, but that's not going to happen. Instead, when we create architectural designs, and what I really want to do is discuss this concept of the architectural design, we think about breaking out the big picture into smaller components. If we're building object-oriented programs, we're going to call them objects. If we're going to build a systems analysis and design approach, we're going to call them entities. And then we're going to apply a different but similar kind of methodology to it. So this lecture, believe it or not, is all about the object itself that's self-contained, and then we have objects that fit into object classes and categories. And this is what you're doing if you're going to do an object-oriented approach. And if you're not familiar with architectural designs at all, take this approach. It's the easiest and the most straightforward. So what I'm going to do is look at how software design may be represented with a set of meaningful interacting objects that manage their own object state and operations. And if you're taking the object-oriented design in Java course, this is week 1. What? A little bit more background information. So it's not a total repeat, but it definitely you'll see some overlap. Describing activities in the object-oriented design process and introducing various models that describe object-oriented designs in general. And then I'm going to show you how some UML might fit into there to represent the models. So I wish I could put a big old sign outside that door that says, "Don't talk out here." But it's right next to the staircase. All right, I'm hosed. Next week we'll be in a different room. All right, topics covered: objects, object classes, object evolution, design evolution. So characteristics of object-oriented design. Objects are abstractions, obviously, of the real world. I'm going to go through this at the speed of light. So stop me if someone's not getting this. I'm going to assume that you either in the object-oriented design course or you've heard some of this stuff already. But everything is an object in the real world. Objects have independent existences, and they encapsulate state and represent information that we're going to store about the objects. So in terms of programming, we always call them states and behaviors, which are the methods and the data, the variables that are associated with it. We have system functionality that is expressed in terms of the object services. So when we create a new component in the architectural design, we just create a new object, essentially. We call it the controller object, the input object, the output object. So everything in your architectural design is an object. So if you start at that point, you just list out the objects. And then we have shared data areas that are eliminated. So shared data areas are eliminated. Objects communicate with message passing back and forth. So we come up with communication that's going to go on. And the objects may be distributed, and it may execute sequentially, or they may be in parallel. There's no telling exactly when. It's just like any live object, exactly when it's going to be used. This is sort of as an example of interacting objects. Your diagram can look like this. So you're going to put together an architectural design for a mine pump water, eliminating mine pump functionality or something. You can actually kind of map it out like this in terms of these little boxes, perhaps. And we could have different classes for different objects. We can have different states, different methods. And this is a really bad object diagram, but it's kind of showing you without using programming terminology. You don't want to write Java or C++ code for your architectural design. The design in assignment number 4 is either going to be an essay in words, or it's going to be a diagram like this, or something similar to this. Don't give me source code. Don't write source code for that. I have actually used this in another class before, and I've gotten source code, which is why I'm saying this. It's not a programming assignment. So. All right, so here we have state, we have methods, behaviors underneath it. If you don't understand what those are, don't worry about it. This is actually a UML class diagram. It's a real crude one. Advantages. It should be hopefully easier to maintain. Objects are understood, standalone entities. Hopefully, objects are appropriately the reusable components. Hopefully, it's maps to real-world abstractions. In terms of the development itself, the analysis, the design, and programming are all relative but distinct, which means they're all different stages. So, in terms of how you can apply object-oriented design, you don't have to do the programming. You can just do the design, which is why I don't want you to write source code for this. I want you to do the actual architectural design, which is composing of figuring out which objects you're going to want and how the objects are going to communicate with each other. If you give me that, that's all I ask for. So you don't have to have an elaborate design. It could be a very high level of abstraction. In fact, it could be just at the object level. See, OOA, object-oriented analysis, is concerned with the development of the object model in the application domain. The OOD is the design part of it, developing the model, implementing the requirements. OOP, object-oriented programming, is the Java or the C++ source code. So I asked for analysis or design, but really I want is the design. The analysis is going to lead into the design, essentially. So we have the entities in the software which represent the real objects. This looks like a repeat. Oh, no, we don't. Objects might actually create other objects. So you can give me the object hierarchy as well. In fact, if you're taking the object-oriented design course, this would be a good practice exercise to put together a class hierarchy and to figure out how the inheritance would logically work, or should logically work, in terms of the implementation of the design. And so what you want to do is you want to list the inherited attributes and services from the other object classes. And the object itself is the entity. And I'm kind of going to go through this a little fast, but make sure you downloaded slide set number 10. You can read through it. When you're doing the assignment, you're going to go back and say, what in the world was she talking about? You can go back through and read the text of the slide. But the object entity itself has the state. So that's why you have those 3 components of the class box, where you have the object name, its state, and then its behaviors, so that you can list all 3 components of it. You do want to make sure you put labels on this architectural design. And you can call them objects, you can call them by names. You can say elevator controller, or pump controller, pump, mine, cleaner, whatever it is you put into this. And you're going to have to use your imagination. I mean, unless you actually have worked in a mine before, you have experience pumping water out of a mine, which none of you probably are going to have. You're going to need to use a little bit of ingenuity. You're not going to be given everything you're going to need to know, so you have to invent that. So the objects are created according to the object class definition. And let me give you a little background on the UML and how we're going to apply it to this architectural design. If we could keep the noise down in the back. Unfortunately, this room has really bad acoustics to it. And you're almost as loud as I am, probably louder. Thank you. Okay, there's several different notations. UML is not the only one. It's the most popular, however. Again, back from the 80s, 90s. It's an integration of notation, also of styling. It's also the de facto standard of what we're seeing today. If you were to write this in a UML fashion, this is what it would look like. You can give this to me in your architectural design. Draw a little box that looks like employee object class. Call it an object. It is an object. You're giving me objects. You're identifying objects. So this could be the mine, let's say. And the mine is going to have a location, maybe. And if you're an employee, you're going to have a name, an address, a date of birth. These are all of the states, as I mentioned earlier, that are in the top box. The box below it are going to be the behaviors. You don't have to put the little opening and closing brackets next to join, but when you do that, it looks like a method, it looks like a function. It's easier to read in terms of the notation, and you don't have to label it. If you don't want to do that, you could put labels. You could put states, behaviors, or you could put methods, variables, or data members, or fields, or however you want to call them. There's tons of words for it. Nothing is correct. Everything is appropriate. So after we take the first step and we identify the objects, which is going to be step number 1 in your architectural design, that's how I would approach it. Identify all those objects, and then figure out how the objects are going to communicate with each other. And then what ends up happening is you go, oh, I need more objects. It's kind of like, I usually use it, in Software Engineering 1, I talked about an elevator example. In fact, I've already covered object orientation in Software Engineering 1, which is kind of like why I'm going to hopefully skip through it, because what I really want to do is, refer to the architectural design. But in the first course, we had an elevator example, and we drew everything out. We discovered, oh, we need an elevator controller, because we have an up button and a down button, and we have all these other features, door open, doors closed, but we have nothing to control any of this. So I guarantee it, you're going to need a pump controller in your mine pump to get control the hose to take the water out. You're going to have a device to suck the water out of the mine. You're going to have devices to do all sorts of the different functionalities and the behaviors. So conceptually, objects communicate by passing messages back and forth. Those are the member functions or the behaviors. Messages are the name of the service represented by the calling object. And we get copies of the information that are required that need to be executed. So we pass information back and forth, and practice messages are also implemented by procedure calls. You can call them methods, you can call them procedure calls for the purposes of UML and design. So the name is the procedure name, the information is the parameter list. What is the method taking in, what is the method giving out? Here's an example, and this looks like programming source code. Call a method associated with a buffer, the object that returns the next value in the buffer. So v is equal to circular buffer.get. Don't write them like this. This is source code. This is too programming related. Write them in a list sort of like that in terms of the bottom box is what I'm talking about right now, where it says join, leave, retire, change details. That's what I want to see in your diagram. I don't want to see that in your diagram. So we have generalizations and inheritance. So hopefully we're all familiar with inheritance at one point. Generalizations are a little different, but they kind of fall into the same association between objects that I've maybe have mentioned. So objects are members of classes, define attributes, different types and operations that are associated with each one of the objects. We have a superclass and a subclass. If all of this is brand new, you go back to Software Engineering 1 notes. I have a couple lectures on object-oriented design. We'll fill you in and bring you up to date. In terms of the hierarchy, you don't have to say subclass, superclass. You don't have to mention anything when you draw this out. Just draw them in a hierarchical order. Put one below the other, and then we can kind of tell that's a subclass, a subclass, a subclass, and we know which ones are the super. You can also draw lines that connect the objects themselves. So the classes that inherit attributes and operations don't reinvent the wheel. So if we have a class employee and then underneath it we have a class janitor, well, janitor is also an employee, so just add the new stuff for janitor underneath it. Those guys who are in the object-oriented design class know this already, but you're complementing and you're adding to the behavior in the hierarchy, so don't repeat it in terms of your class diagram. The generalization in UML is implemented as an inheritance in the object-oriented programming language, and it refers to the generalization that employee, janitor is also an employee, so built in with the hierarchy and so the generalization here. Generation, we have the employee, manager, programmer, two types of employees. And this is an excellent example of your architectural diagram. But it's not of a mine shaft or water or anything, it's of employees. So we have an employee on the top. You don't actually have to put the arrows in there. In fact, it's kind of odd that there are arrows in there. Normally you won't see that. These arrows will be gone, actually. But what we're looking at here is the main head guy, the main object, manager, programmers, which are also employees. Of a manager, we have a project manager, a department manager, a strategic manager, different responsibilities, departments, and projects associated with them. So slide number 15 is an excellent example of what your finished product for assignment number 4 is going to look like if you're taking this approach. You do not have to take this approach, however. You can take any approach you want. Advantages of inheritance, obviously reuse. You're essentially taking advantage of everything that exists without having to rewrite new object definitions, new objects. What we have is a bunch of objects. Why not inherit? Why not use it that way? The abstraction mechanism is also used to classify entities. Because of our generalization and our generations, we know that a strategic manager is also an employee, which is where that terminology is coming into play again. And the inheritance graph itself is a source of organizational knowledge about the domains and the systems. This gives us the knowledge just the same way as an organizational chart at a company tells you where you sit in the hierarchy and where your manager sits and everything. It has the same purpose in sense of the hierarchy. Problems with inheritance. Interesting thing. Objects are self-contained, or they should be self-contained. They cannot be understood without references to their superclasses. So you have to actually know the hierarchy in order to figure out what is being inherited, what is being referenced. So designers have a tendency to reuse inheritance graphs created during the analysis. Can lead to a significant inefficiency. This is where I say when you map out your first object list, you're going to want to change it. Because what you're going to look at, in fact, another approach you can do is just, instead of drawing boxes, just list out all the objects. And then to the next time, write a little notation to yourself as to what the functionality is supposed to be. This object represents the mine itself. Okay, inside of the mine we have the left shaft, right shaft, or whatever we have in terms of the components. And then, you know, as you get through the list, you'll see some duplication. And you'll go, well, mine shaft, isn't that the same as this down here? And then you start crossing items off of the list. And then you start looking at the list, you go, okay, now something's missing. And what's really missing is something that's not in the description, but something that you need, like a controller, or something that oversees some activity, or some class that actually joins two other classes together somehow, which is in between the lines, which you didn't read in the description, that you're going to need to add to the diagram, or add to the list. So it's kind of a brainstorming technique in a lot of ways. In fact, the concept of creating that class diagram is a brainstorming activity. Nobody ever creates a perfect diagram the first time around. It takes a couple of iterations through the diagram to actually get it correct. So the inheritance graphs of analysis, design, and implementation have different functions and should be separately maintained as well. So what you put together in your analysis is not necessarily what gets done in the class diagram. And here's the key to the whole concept. Unified Modeling Language, UML, works with objects, works with classes. You might think, well, an object is a class, kind of, because we're all taught in programming that we implement objects by creating classes. But they are two distinct, separate concepts. What you're giving me in the architectural design is an object level diagram, part of analysis. Objects turn into classes in terms of the design phase, and that leads into the implementation of the source code writing. Two separate concepts. There's object diagrams and then there's class diagrams. You see more generalizations, you see more loose interpretation in the analysis through those objects. In the class diagram, you see more specific methods, data members, and you have it's stricter. So if you follow the design off of the design, then you're good. If you follow it off of the analysis, you can actually take that and turn it into a couple of different designs theoretically, depending upon what responsibilities you want to give each one of the classes. In the objects, you're doing a higher level architectural. Going back to the definition of architectural design, our theme for today, it's high level. If you looked at a network diagram that was an architectural, you'd see a cloud, and it would be called the network. And over here you see another network. Over here you know, lines connecting the networks. You're not really seeing the inner details of what's in there, what protocols are being used in these different networks, and what computers and what servers are being connected together. Instead, it's raised up a level of abstraction, and you're just seeing the cloud. So when you think about your architectural design, raise it up a little bit, and you can use classes if you want. I would prefer to use objects, actually, and just put this object out here, and put this object out here, and put this object out here. you're not at the source code writing stage. So you're not going to take it down to the design where you're writing the methods. So going back to this here when I said it's going to look more like that than it's going to look like that. That's a class. That's a class because we're saying join method, leave method, retire method. A lot more detail than is really needed for an architectural design. That would work well in a class diagram. That would work better, and still it's a lot because it's written in a cryptic kind of language. You could take that up a little bit higher and say, get rid of this part right here, if you wanted to. That would actually satisfy architectural design purposes, where you're not setting in stone which methods and which data members and behaviors, because that's a class. You're defining a class. Here you're saying we have an object, it's called the manager. Because you could drive yourself crazy with that example with the mine, going through and coming up with methods and data. I mean, at that point you might as well just write the source code. But you're not taking it to that level is what I'm trying to say. You're taking it just from an analysis to a preliminary kind of design with an architectural representation where you've got object 1, object 2, and you actually can give the objects numbers, which is interesting. You'd never do that in a class diagram. In fact, people give the objects numbers so they can refer to them. So you can have a template, or not template, you can have this particular diagram, and then you can have like a 1 up here, 2, 3, 4. And then on another sheet of paper, you can say 1 defines the existence of the employee object and everything associated with the employee. Number 2, because you don't want to write this in the diagram, so people do this with legends. They'll color code it, they'll number it, they'll put descriptions like something budget controlled, date approved. They'll put like the pseudo kind of writing in here, which isn't really English. It's telling us, department, but it's not really, is that apparently it's a data because it's of the way the boxes are designed here. This is sort of a mixture because it's written in a class diagram format, but it's an object diagram. Class diagram objects, you can point them out because of the 3 boxes. Objects don't normally have the 3 boxes. Usually you see 2 because we don't have anything down here on the bottom. So the 3rd box is kind of empty. I mean, it's going to be empty. Why put it in there? So sometimes, that you can look at it and go, well, if it has 3 sections, it's a class diagram. So you don't want to don't give me a class. If you give me a class diagram, you're going to lose points for it, but you've done a lot more work than you actually had to. You can make it a lot simpler for yourself. So, let's see. We need to talk about problems with inheritance. I think I covered that already. Different functions should be separately maintained. We might inherit from the analysis, and instead of the design, we might have different design methodologies that we don't think about. We might have wrong inheritance. Inheritance in the object-oriented design is difficult. The differing views as to whether inheritance is fundamental to object-oriented design, or whether it's an analysis concept, or whether it's implementation. View number 1: identifying the inheritance hierarchies or network, fundamental part of design. Obviously, this can be implemented using object-oriented programming languages. Think about it. But what if we're designing for a language that doesn't support inheritance or supports multiple line inheritance or doesn't have the same? Because theoretically, when you're putting together this design, you're using object orientation as a methodology, and you're not thinking about any programming language at all. You're not doing this in Java or C++. You're doing it in language X, which is object orientation. So there's a controversy in thought because object-oriented languages all have different similarities. They have some similarities, but they also have some different implementations of the inheritance concept. So is it proper to put that into a higher level architectural design? You can. However, you might notice that you may not be able to implement the design appropriately depending upon the language selection. So it's just a caveat right there. View number 2 says inheritance is useful implementation concept. Allows you reuse, identifying inheritance hierarchy and design stages, places unnecessary restrictions on the implementations. Because what you don't want to do is highly restrict the code that actually can be written from the objects. So you want to make sure you can have flexibility, freedom of interpretation as well. So inheritance basically introduces complexity also that's undesirable. especially in critical systems. You want to make it as simple as possible, which is why you're doing the diagram. So let's talk about the associations, another concept you're putting into the object diagram. So you have not relationships, but associations. And I talked about associations in Software Engineering 1 as well, but to refresh your memory, objects and participate in relationships with other objects and other classes, and object classes. So you're saying, what was an object? What was an object class? Well, we have groupings of objects that end up in object classes. It might turn into packages, might turn into other concepts depending upon the language, but we're not there yet. We're not implementing it in a language. We're just thinking of the concept. So we have the generalized relationship that's indicated by an association. That's another word for the relationship, but it's not a cardinality relationship. This would be associated with a procedural or structured analysis and design approach. In object orientation, it takes all that stuff away and says there's an association. Like they know each other, but they don't have a relationship. It's an association. It's kind of like being friends or best friends, I guess, one or the other. We're not defining the relationship because there's an association. So it's a general, but may indicate an attribute of an object is an associated object, or that the method relies on an associated object. Like one method actually needs the other object, otherwise it can't perform its functionality. So, like the call to something needs something else. So here's an association that's modeled, and this is where those people who know about entity relationship diagrams are looking at this going, looks like an entity relationship diagram. It's a variation. Because, again, going back to the concept, we're not showing relationships. We're showing associations. So the employee is a member of a department, is managed by a manager who manages it. Very similar in concept. You won't see triangles or, those diamond symbols in this type of diagram because that's an entity relationship symbol. This is associations. In fact, you usually see it as is a member of, is managed by, because that describes the association in terms of the complexity. Concurrent objects. So you're showing the objects, showing the associations between the objects. You're listing out any type of data that might be associated with the object. And you put that inside of each one of the objects, and you draw them together to show the association and also to show the hierarchy if you're going to show it. You don't have to show me the hierarchy if you don't want to. You don't have to use inheritance at all. Concurrent objects. So it's the nature of the object, a self-contained entity, makes suitable for concurrent implementations. So our message passing model can be implemented directly if objects are running on separate processors and distributed systems. Uh-oh. This is where we can branch things off. So when you see an architectural diagram for a systems analysis and design, scratch object orientation completely. Prior to object orientation, you saw boxes. And you saw server 1, server 2, cloud 1, internet connection here. And it was architectural design of the different subsystems that were all connected together. And this is where those nice little symbols about what a database looks like in the real world. I've never really seen a database. There's no picture. All the pictures are like this little cylinder thing. You see those on the diagrams. It looks like a database. And you see printers, and you see all sorts of different other objects on there. That's the traditional style. We're sort of doing the same thing with our UML and our object diagram because we're still doing an architectural design. So we can show example servers. So we got a server, and the object's implemented on one server that's communicating with another server. If we were implementing a distributed system, we'd have multiple servers. I don't know if your mine application is going to call for this. I didn't read through the description, and maybe that was a good idea not to read through it. But you can read through it. You may have parallel processing going on. You might have concurrent servers running together. You might have different mines that are being managed concurrently together. I don't know. Depending upon the situation, the object is implemented in a parallel process on another server. And with entry points corresponding to the object operations, no calls are made to it. The object suspends itself and waits for further requests from another server, so it communicates back and forth. active objects, we could show active objects or inactive objects in terms of what's going on in terms of the state. So the object state may be changed into itself, not simply an external call. The object itself might actually change itself to say, I'm waiting, I'm ready. Nope, I'm busy, I'm processing, leave me alone, or something of that nature. So active transponder objects. Now this is sounding like Star Trek or something. Active objects may have their attributes modified by operations, but may also update them autonomously using internal operations. So if, let's say for example, the mine had a pump that was pumping water out of it, and the pump had a storage container, the object that's representing the pump might have an association with a storage container. The storage container might get full as the pump is pumping water into the storage container. Then that would be an example of an active transponder object in which the object itself is monitoring its own state. It's saying, I'm full, sends a message back to the object that's using it, the pump. This is the container that's storing the water, sending a message back to the pump that's going to say, turn me off, stop, give me another container. We fill up multiple containers. Maybe we have multiple instances of the container object that gets created in this diagram. So then we can kind of show how this object might tell the other object to do something. Give me a new container. Or, I'm full, leave me alone. And it might actually represent its state, or maybe it goes through a process. Maybe there's a hole in the container and you open it up. Not like a what do you call those things? You go to the beach, coolers. And you put the ice in the cooler and it fills up with water and you pull a little cord off the side of it and it empties it out. Yes?
I just couldn't get the letter done. He told me to come by 3.
Okay.
Okay.
All right.
I'll be back.
Oh, no problem. So the transponder object broadcasts. Here we're going to broadcast an aircraft's position. The position may be updated using a satellite positioning system. The object periodically updates the position by triangulation, whatever, from satellite. So in this particular example, we've got a satellite, let's say, that's controlling an object that's communicating to a satellite to say, hey, I'm over here, I'm over there. We might have a container that says, hey, I'm full, stop putting water into me. So we can represent that in the diagram and in the object itself. Here's some source code for the satellite, actually, where we've got a position, current position, we have coordinates, and we can basically have a satellite kind of navigate us or track our coordinates. A lot of these things are actually implemented in the form of threads. If we think about concurrent programming, multi-programming, we have threads that come into play. In Java, threads is an example. It's a simple construct for implementing concurrent objects. You could show threads. In fact, there's a UML diagram that gives us a thread diagram. It shows us which threads are running, which ones are actives. We can mix that in with a state if you want. You don't have to. In fact, most likely, I don't think you're going to be dealing with a multi-threaded architecture. I haven't read through it. I probably should. But I don't think you're going to have to run through that. And if you do, you can just show it in terms of, here's an object, ... or something, or here's an object times with a question mark. I don't know how many of these objects we're going to need to hold the water. It depends on how much water we get. So to represent the unknown. Or you can actually show it in terms of active objects, typically include infinite loops, so they can carry out computation, and inside of the loop we might actually have a thread that gets spawned that does something. So the object-oriented design process. So we design the context of the modes and use them in the system, design the system architecture, which is what we're doing in this model. We identify the principal system objects, develop the design methods, and specify the object interfaces. We're not doing all of this for the assignment. What we're doing for the assignment is it's not really steps, it's more like concurrent activities that occur. We're looking at the system architecture. And here's the big aha, this is why people like object orientation. Old days, you do system architecture, and then you do model of something else, and you do model of something else, and then and finally you get down to something that you can turn it into source code, maybe. But you're looking at this, and you're putting all the pieces together. This naturally lends itself to the source code eventually. So from the object diagram, the sequence diagram, the interaction diagrams, all the different things, what you end up happening at the end is the class diagram, which is kind of interesting because people like to draw the class diagram first, when it's really the objects that they're thinking about, and that they're trying to design is the object interaction and the object. But they're already designing the classes at that point, so they've skipped all of the methodology all the way through, and they've skipped the analysis, and all they're doing is the design, or the programming, actually, is what they're doing. So what you're doing here is at a higher level, you're just identifying the objects, and you're just identifying the associations. We could develop the design out of that and specify the interfaces between them. There's a weather system description that follows along, and what we're going to do is take this and do a little bit more than what you have to do for that fourth assignment, because we're going to go through all of this particular process. Won't take too long, actually. And see how it actually works together, put all the pieces together, and kind of show you the process in terms of the methodology. So the weather data collection system is required to generate weather maps on a regular basis using data collected from remote unattended weather stations and other data sources, such as weather observers, balloons, satellites, all sorts of things out there. So we're collecting data. The weather stations transmit their data to the area computer in response to request from that machine. So their machine requests the data, it transmits it. The area computers validates the collected data and integrates the data with other different sources. And then the integrated data is archived and is used. The data is archived in digitized map data, sets weather maps, and creates maps out of that. The maps are then printed and distributed on a special purpose map, printed or maybe displayed on a number of different formats. So we're taking data and we're creating a map out of it. And the data's coming in from a bunch of different sources. So it's not a complicated system. So the system itself is a package of software-controlled instruments, which collects, performs some of the data processing, transmits the data for further processing. Instructions include air and ground thermometers, and an anemometer or whatever, a wind vane, barometers, range gauges, all sorts of different equipment. Data is collected every 5 minutes, so it's happening a lot. And when the command is issued, transmitted the data itself, the disk processes it, summarizes it, collects it, transmits it. Summarized data is transmitted in a mapping computer when a request is received. So here is our layered architecture. Right, don't hold your breath. Just wait for a second. It'll all come together. What we've done is what I referred to as concurrent. Sometimes it can be applied to the concept of concurrency. And if you have a single system, you're not going to do this if it's all on one level. This has got some different levels to it. So you could start out with a layered kind of look to the whole system and go, okay, well, what's number one? The subsystem, we have the data display, the data archiving, the data processing, the data collection. You don't have to represent it this way. It's just represented in forms of higher layer abstraction. You can read through, as an example on the top here, the data display, the layer where objects are concerned with preparing and presenting the data in the human readable form. And here we have the data archiving layer where objects, so what are these? These are categories or packages of objects, which is why we have this thing that looks like a vanilla folder. It's a package, if you're familiar with Java, or actually any language, it's pretty much the same concept. It's a grouping. So these are object classes. You don't have to actually take it this far. You can actually draw your objects inside of each one of the layers and skip this outer package that's associated with it. But this is an example if you were to kind of create the layering composition of the system, which is step number one, breaking everything out into the objects and finding out which object category does it fall into or what layer, using this terminology. So now we're going to develop an understanding of the relationships between the software being designed and its external environment. We can look at the system context. So we have a static model that describes other systems. We can use a model of the system use. So now you're actually looking at different levels of abstraction that can then be applied towards the design. And remember, just keep in the back of your head, the only reason why you're doing any of this is because you want to understand the system. You're trying to gain a better understanding of it. So if you don't want to do or actually you would probably start out with a lower level detail, I'm assuming most of you would probably do, in terms of that representation. And then, hello, here's our subsystem in the weather mapping system. So what do we got? We got subsystem data collection, data display, data archiving, data processing. Well, it looks like that. 1, 2, 3, 4. 1, 2, 3, 4, all connected together. Don't give me all of it unless you want to create a lot of work for yourself. You're probably not going to do that. That's too easy. You're probably going to think there's a trick to it. Instead, most of you will probably do something like that. That's going to outline in terms of the way you're going to present it to me in your deliverable. You're going to say subsystem, or you're going to say data collection. Data collection is going to have an observer, a satellite, a balloon, a weather station. You don't have to use those fancy little package symbols. You can just draw boxes. You could take it a step further and put information inside of those boxes if you wanted to. You don't have to. You're giving me objects. All you're doing is representing objects, and you're going to layer it, or you're going to present it at some sort of connection. And it's really simple, actually. We've got lines that are connecting just to show the association. I don't want to see any cardinality or anything like that. You could put messages. You could put, is an instance of, or uses, or sent to describe some of the activity of the association if you wanted to. But this is what the subsystems in the weather system mapping would look like. And this obviously is taking the approach of systems, which is the architectural design. It's the systems. This system working with this system, working with this system, and it's the combination of all the systems working together that give us the program. So we have our use cases. This is pretty easy. We've seen these before. Nobody's really scared of this stuff. Start, stop, report, calibrate, test, which is easy. And then we have use case descriptions. Now keep in mind, we're not doing all of this. That assignment is only asking you to do this. I just showed you that. Those are the objects, either they're layered or okay. But this is going to go through the whole design. This is going to put all the pieces together to show you how this works together. So that's only one component of it. We're going to take a look at the use cases normally, if we were going to do a full design on this, and write up some use case descriptions. We do this so we can document it, and we can incorporate this information, because we're going to eventually go back to here, and we're going to make a class diagram out of that, because that's an object diagram. We're going to put all the stuff in the object diagram, make it into a class diagram eventually. So the architectural design. Once the interactions between the systems, you don't have to document this, but once you know the interactions and its environment have been understood, analysis, not design, you've understood them, use the information for designing the system architecture itself. The layered architecture is appropriate for a weather system. You don't have to do it. You may not have a layered approach. You don't have to use it, but it would be appropriate for this particular design. Interface layers for handling communication, data collection layer for managing, instrument layer for collecting data. Think of it as a level of abstraction. There would be no more than 7 entities. And again, they call it entities. Probably should say objects. Entities are objects in an architectural model. So what do we got here? We have 4. So what this is saying is, on average, we don't have more than 7, usually. So if your architectural model has 12, 15, 20, you probably need to scope that down a little bit. Make the objects a little bigger. So you should have more than 7. I don't know where that 7 comes from either. Depends on the type of system, personally. Depends on how difficult the system is, personally. So here's the weather station architecture. Another way of representing it. We don't have classes here. We have objects. We have the interface, the data collection, the instruments. We have little notes. These are notations in UML, actually. It's like a stick-em note. That's why they're yellow. A stick-em note. Manages all the external communications, collects and summarizes the weather data. You can do that if you want. You can actually put little notes on the diagram like that if you wanted to. So in terms of the object identification or the object classes, that's the most difficult part of the object-oriented design part, figuring out which one of these you're going to put in here. And another notation I might mention is I've been going back and I've been referring to this as the architectural design. I've also referred to that as the architectural design. I've also referred to the object method. They all fall into the same category of architectural design. There are some researchers that would call that the only architectural design, which is a loose interpretation, actually. So what is actually referred to as the architectural design is the high-level overview of the system. If you present it like that, it gives me the same information as that. That actually gives me a little bit more detail. But you might not be able to understand the system to that point yet to know about all the subsystems. That, is actually sufficient. Because you can't take and you cannot create the system from this architectural design. Impossible. You don't have enough information. It's not meant to be used that way. So it works with the other components to create the design, but you don't have everything in there. So I guarantee you I'm going to get assignments that have classes with source code and everything's all mapped out, which is not going to be the purpose. All right, so object identification. There's no magic formula for the object identification. It takes a lot of skill, practice. Actually, practice is probably the best thing for it. You're not likely to get it right on the first time. You're going to take many iterations through to actually kind of figure it out. Approaches to identification. In fact, we did this in Software Engineering 1, and the noun abstraction, or the grammatical stuff, is actually pretty much used a lot, using the natural English words in the description. The router is connected to the, and then router, connected to the, and you start putting the pieces together. Base the identification on tangible things in the application domain. If you don't want to use the English wording of it, you can just say this object, this object, this object, this object. There's no science. There's no science to it. Use a behavioral approach and identify the objects based on their participants in the behavior. Maybe if you want to do it that way, you can use the use case scenario analysis. Draw out the use case scenarios, the objects, attributes, the methods that are in the scenario that are identified. In terms of the weather station object classes, we might end up with ground thermometer, barometers, I can't pronounce that word, anemometer or whatever. The weather station itself, the weather data, that makes sense. So in terms of an object, so weather data would be all the summarized data in each one of the instruments. That is a class diagram. It says object classes. So now I wish I could edit, well, I probably will end up editing this because it causes confusion. When I edit this, I'm going to do the exact opposite of what I did at the beginning where it said object classes. It said the same thing, but I'm going to scratch the word classes off on the slide number in the beginning that showed us the objects. And then here I'm going to cross out the word object and say this is the weather station classes. Because we're looking at all three sections. We're looking at the methods, we're looking at the data. We're actually looking at the classes that we would create from the objects that we have identified. Further objects and further object refinement. This is when we take this and we go, wait a minute, we're missing a controller. We're missing something to hold it together, or we're missing another piece of it. So you use the domain knowledge to identify more objects and more operations that might not exist. And for those people who like structure, for accounting people, this is really bad because there's no structure to this. Methodology is left to interpretation. So the weather station should be a unique identifier. Maybe the station is remotely situated in instruments. Maybe there's some failures. Anyway, active and passive objects. All sorts of different things can be added to it to further refine it. And then we design models. And the models themselves can show, an example, classes and relationships between the entities, static models describing the static structure of the system in terms of the objects and its relationships, dynamic models showing dynamic behavior between the interacting objects, examples of the design model, subsystems, sequence, state machines, and others. I went over this actually in the UML overview in Software Engineering 1. From this stage, when we've identified, then we start modeling in all sorts of different ways to show the state, the sequence, the behaviors, anything we could possibly imagine about what might be appropriate We do that so we can get a better understanding of the system. The design models helps us refine the class model, helps us show where things might be missing. Subsystem models, also important, showing how the design is organized in terms of its logically grouped objects itself. In UML, there's also shown using packages as well. We've seen that already, encapsulated constructs. So we can organize things into different packages, and packaging might be different. Here's our package actually model showing us weather station subsystems. Now this one says weather station subsystems on it. This one over here says weather station subsystems on it. Oh, nope, that one doesn't. That one says subsystems on it. It's actually kind of the same. It's the same model. It's just drawn a little bit differently. That's one of the interesting things about UML is that you see so many different interpretations and so many different lines and formats. It's not standardized. It's unified. It's not standardized. Otherwise they call it standardized modeling language, but it's unified. Brings things together. So in terms of the sequence model, an example of that would be this one. We've actually kind of seen these before in Software Engineering 1. So what we're looking at now is examples of each one of the different system models that we could put together. State charts, that one here, we've seen that before as well. It kind of reminds me of a data flow diagram, actually. It goes from kind of like an on or an off or left or right routing through the system. From a state one, we can, actually I think that's all the pretty basic ones that we can look at. Sequences, states, packages, things of that nature, state charts. Other object specifications, we can go back in a little detail and kind of put a magnifying glass up against our object and say, let's look at the interfaces. Interfaces are usually left for last because once we define the objects, we know their interactions, we know their relationships. Then we start looking at the interfaces between them, and in terms of the interfaces, we can specify out the components in the design. So we avoid designing interfaces representations that should hide this in the object itself. And we want to make sure that the object, when it's implemented, can create its own interface. We might have several different interfaces, which are viewpoints on the methods that are going to be provided, different access methods. And UML uses class diagrams for interface specifications, but Java may also be used as well. In fact, this is where we start writing code at this particular point. At the time we start looking at the interfaces, we're practically writing the templates for the classes. And here is an interface where we have interface weather station, and if you're in the object-oriented design class, this is giving you an interface example again. So I know some of you guys are in that class. So this is how the interfaces actually come into the design process. When we know we're not writing any source code, we're just writing a template that says we're going to have this method, we're going to have that method, we're going to have that method. And what does that define? The access, the public, the private, the protected, all the access methods and all of the things that we know are going to be implemented in that particular object. So bringing it around, we have the design evolution, because we know the first time we put this together, it's not going to be right. So we take it around and we do it again, and we do it again. So we hide the information inside the object, means that we changes that are made also to the outside of the objects don't affect any of the objects in any other predictable way. So this gives us evolution, it gives us reuse, it gives us a design that can evolve because we can add objects to it. As long as we keep the interfaces consistent, we can grow the system, shrink the system, redesign the system, and all the existing objects can stay as is and it can still be used. Some population of monitoring facilities are to be added to this weather station. We're going to upgrade it. Might have some samples of the air. Might compute the amount of different pollutants in the atmosphere or something. So the readings might be transmitted with the weather station data. So, in terms of changes that might be required, adding an object class called air quality, maybe as part of the weather station. So it allows essentially growth as well as reuse in terms of the design, which is another reason why people like object orientation. It allows for a very flexible design that can be maintained and it also can be expanded in the future. So adding an operation to report the air quality, adding other methods to it, adding objects representing pollution monitoring that might happen, might come in. And here's an example of some of these methods that can be added to it. Normally what we would do is we would provide separate architectural design, separate diagramming to represent some of the additions or changes that we're not going to put in. So, all right, I know you guys are getting restless. I can hear it in the back. Let's go to the summary here, the key points. And how are we doing on time? Oh, we're doing good. So object-oriented design itself is an approach to design so that the design components have their own private state and operations associated with them. We are creating interfaces between objects. We are defining them as separate entities. Objects should have a constructor and inspector operations. Didn't really talk about the programming aspects of this, but these are some of the things we want to implement as we're creating the class diagram and the structure of those objects. And we also want to think about how objects might provide services to other objects that might be in the system. Objects might be implemented sequentially or concurrently. They might be running actually sequentially, or they might be running concurrently in the system. And we can show that by either using a layering approach, or we can use a sequence diagram, or we can use all sorts of different techniques to represent that concept. Unified modeling language, UML, provides different notations and different object models. And so there's really no de facto standard in terms of what is required for the design. What there is essentially is what is going to be needed to understand the system. So a range of different models might be produced during the object-oriented design process. Might be static, dynamic system models, might be any type of system model. Interfaces should be defined precisely using the programming language, and that's why they're always saved for last. Because at the beginning we don't necessarily know what language we're going to implement it in, and so we write the interfaces in whatever language as a last kind of step. And the design simplifies the system evolution. So it describes it, and then in the future we can evolve. In that last particular example I showed you with the weather station, we can add new components to the system to make it evolve into something else. So that was the first part. What? We're not going to do it today. But let me just preview what we're going to do next week. Because you might want to wait. I don't really have to wait. You could probably do assignment number 4 anyway without it. Now, I'm hoping you're going to walk away with the impression of what an architectural model actually is supposed to be in context. So that was lecture 10 if you want to download it and look at it in a lot more detail. Lecture number 11, which I'm going to save for next week, we still have 2 more lectures left along with our review before the final. This one's going to get into the concept of reuse, and it's going to talk about design patterns for reuse, which is going to help you in terms of the architectural design, but you don't really need it. You don't need this information. You can probably come up with your own object diagram without thinking about reuse. And here's the interesting thing. In terms of the assessment on that particular assignment, it just asks you to come up with a design. Whether your design is right or wrong, there's no right or wrong answer to that, first of all, because nobody who actually comes up with an object architectural, you can't build the system from an architectural model, first of all. You don't have enough information. You're taking the architectural model is your first stab at getting something on paper that identifies the components that are in the system. And if you're using an UML approach, which you don't have to, but if you're taking the object-oriented approach, all you're doing is identifying objects. Look at the beginning of that slide system when I pointed out some of those diagrams. You're just creating an object diagram. That's your architectural model. Your system architectural model is very high up. Those people who aren't listening to me or who aren't here today are going to map out source code. They're going to have classes. They're going to have everything. You can spend months. Actually, you can spend about 6 months diagramming out, do the object-oriented analysis, object-oriented design, and the object-oriented programming for this entire thing. We're taking one first preliminary step in the object-oriented analysis part of it. But it kind of shows you every project that you're going to scope out is going to have an architectural design. You have to have some way of showing what the system is on paper. And it's the highest level of abstraction that exists. Everything else is the lower level, till you get to interfaces, and then you're writing source code at that level. So, questions? And I'm so glad you actually mentioned, because I totally forgot that assignment dealt with art. Yeah, so it was a good thing that you mentioned that assignment. I'm thinking, I know we had something that related to it. So. All right, unless we have any questions, I believe we are done for today. Enjoy the rest of the sunny day.